Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. What's a great story that's happened in science this week, Dave?
They've found ice on an asteroid. Now, asteroids are sort of small lumps of rock and stuff. There's quite a lot of them between Mars and Jupiter.
Yep.
And they've been looking at one of these asteroids using an infrared telescope. And you can measure the light coming back on it, and different substances reflect different colours of light differently well. And they've noticed quite a lot of water on it, on the surface. And they've seen organic compounds, so things with carbon and hydrogen, the sort of thing, which building blocks of life. And this is quite surprising because from the sort of temperature it is out there, and it's a very, very hard vacuum, so water ought to just evaporate. Even ice, it should evaporate. So they think it must be being supplied from possibly inside the thing. So it's not just a crust on the outside, it's getting supplied somehow.
Yeah.
And it's interesting because it could be that these are all building blocks of life, and it could be that the building blocks of life on Earth, which were created, could have been supplied by asteroids, because there was a period of very heavy bombardment by asteroids and comets and things, and during the Earth's early life. And so if it's bombarded down, they're going to bring down lots and lots of water and lots of these organic compounds, which could have just by chance somehow started reproducing and eventually got life.
There could be somebody up there living in a little cave somewhere.
There are also other theories that life could actually have been transferred to Earth on things like this. So it could have started off on another planet or another sort of planetoid, and then got transferred through space and then crashed into Earth from an asteroid. They've actually taken bacteria up onto satellites, and they've sort of had some types of bacteria sitting out in full sunlight, and sunlight coming directly from the sun, which hasn't been filtered by their atmosphere, is really nasty stuff. Yeah. There's lots of ultraviolet light in it. It's really, really destructive for anything living. But bacteria survived that for several months. So who knows? We might all be Martians.
It's all cosmic. Let's start our questions off then tonight for Dr. Dave. Frances in Peterborough has given us a call, and she would like to know, Dave, how are batteries recycled?
Basically in a very similar way to anything else. The point of recycling is to get out all of the important materials, useful materials which you can use again. So they're going to basically break the batteries up. I don't know the details of the process, but I mean probably by the process of kind of chewing them up and then probably actually taking them apart if possible, so as you keep the lumps of stuff in as big a lumps as possible. And then possibly might have to do some chemical processes just to separate everything out. And then they grind it all up once you've purified it and send it back to manufacturers who want the materials.
He knows, you know. Bob in Essex says, why is it that a red sunset means a fine day, but a red sunrise means a bad day?
Yes, it's the old rhyme, isn't it? It doesn't work all the time, but it's giving you a fairly good idea. It's to do with the way the weather works in this country. Basically, the weather tends to all be coming from the west. So especially if it's ever going to be wet, although the wet rain clouds are coming in from the west. And so you can tell if there's a load of rain clouds coming in from the west, then you're not going to get a nice red sunset because the sun's going to be behind a cloud. However, if you're getting a nice red sunrise, so you can basically, if you can see the sun at sunrise, that doesn't tell you anything about the wet rain clouds, because that tells you whether it was raining today or yesterday. Sorry, not whether it was raining, whether it was clear today or yesterday, because the sunrise is in the east, which is where all the weather goes to after it's been over your head. And I think there is probably a general tendency that the rain, so the rain comes from the west, goes to the east. Right. And if the sun's setting, then it's in the west. And if you can see the sun in the west, it means that there's no clouds there. Okay. Because you can see the sun, and therefore it's going to be clear for a while because there's no clouds in the west. But if the sun is rising, then it might be clear over in the east, but that doesn't tell you anything about what's coming on in the future. And also, if rain clouds are about the same sort of size as you can see, maybe sort of 50, 60 miles across, then if there isn't one to the east, probably it means there is another one coming soon, because of we get so many rain clouds this part of the world. So if you can see a nice sunrise, probably there's a rain cloud coming on the other side of the sky.
All right. Now, our next question comes from Harry, and it's on email. And it's one of those things that I'd never thought about before. But Harry says, hello, what would happen if all the people in China jumped at the same time?
That is a very good question.
It's a bit of madness. Who wants to know that? Go on.
Lots of people talk about that quite often, I think. There's quite a lot of people in China, over 1 billion of them, so let's say 1 billion, that's nice, easy numbers. Yep. So they weigh about 60 kilograms each, which is possibly an overestimate, as quite a lot of them are going to be kids. So that's going to be about 60 billion kilograms, or 60 million tonnes, okay? So that sounds like it's pretty heavy, it's quite a lot of weight.
Yeah.
The Earth is really quite big, though. So the Earth is actually got 6 with 24 zeros after it.
Right.
Kilograms.
Okay.
So if all those people jump up by a metre, the 60 billion kilograms divided by 6 with 24 zeros after it is actually about 10 with another, 1 with 14 zeros after it. So 1 times 10 to the 14th. So it's very... So 1 divided by 10 to the 10 with 14 zeros, 1 with 14 zeros after it.
Has anybody lost time?
So that's 0.000000001 of the distance, so about that number of metres.
Right.
So the Earth overall, if it did move, it would move a minute amount, so small you couldn't measure it. And also the Earth isn't very rigid. So in fact, what would happen is the Earth would probably deform and it wouldn't move as a body, it would kind of wobble and you get waves moving out about it, which is actually what you call an earthquake. And in fact, I worked this out, and if all the energy they used to jump got transferred into the rock, that would create an earthquake of about 4 or 5 on the Richter scale. It's a very small earthquake you might just about notice if you're lying somewhere very, very still.
Let's keep China still then, in that case. No jumping up and down over there. Let's go to our next question. Mike has called in to say, stainless steel, why and how is it stainless? Because I can never get my sauce from stainless. Why and how is it stainless? Thank you, Mike, for your question. Dave?
A very good question. Stainless steel, it's mostly iron, like normal steels.
Yep.
But it's actually got other elements mixed into it, particularly chromium. Chromium is the stuff which makes very, very shiny bumpers. They kind of chrome bumpers, and you get that really shiny kind of 1950s American look. And the reason why it stays so shiny is a particular property of chromium in that it's like aluminium. Aluminium does the same thing. When chromium starts to oxidise, it's essentially the equivalent of rusting, it develops a layer on the outside, a very, very thin layer of chromium oxide, which protects the metal underneath from the oxygen. So it kind of makes its own protective layer, and so it stops rusting anymore. And the same thing happens with aluminium. Aluminium would actually is incredibly reactive, and if it didn't do this, it would rust away in a few days, probably definitely a few weeks. But because it forms this layer of aluminium oxide on the outside, it protects it, and it doesn't oxidise anymore. And the chromium in the stainless steel does the same thing, and you get this layer of chromium oxide on the surface, stopping it rusting, and it's nice and stainless, and you don't have to eat rust on your knives and forks.
OK, thank you for that. I think I'm there with that one. Dominic has said, it's from Newmarket, he says, how and why does cod liver oil help you to concentrate?
That is various people who've been pushing this for a while. There's a little bit of evidence for it. I think there's definitely evidence that there are various vitamins in fish and fish oils, which if you're depleted of them isn't good for your brain. But whether taking lots more of them actually helps your brain is another question. In fact, there was quite a big study done recently in the last couple of weeks where they've done a very big study, and they've found that there's actually no evidence that it has any effect at all. Fish oils in general on people's brain, it doesn't seem to have any effect on the elderly or children if you do a very big study and do it properly.
Now, Dave, I've no idea what this is, but what does Avogadro's number represent?
Avogadro's number?
Avogadro's, yes. What's that?
Avogadro's number is a useful number when you're doing chemistry. Basically, in chemistry, you're interested in reactions between atoms individually. So, for example, if you're reacting hydrogen with oxygen, you need 2 atoms of hydrogen to react with 1 of oxygen. You also need 2 molecules of hydrogen to react with 1 of oxygen, and they react together to form 2 molecules of water. Now, that's very useful if you want to work out the ratios, the numbers of hydrogen atoms. So if you know that two molecules of hydrogen react with one molecule of oxygen, then that's great. The problem is that the numbers get really, really silly because there are about 6 times 10 to the 23 atoms of hydrogen in 1 gram of hydrogen. So if you wanted to react 1 gram of hydrogen with some oxygen, you'd have to work out how much mass of oxygen. And then the numbers, you'd have to multiply everything by 6 times 10 to the 23, and you'd be reacting 6 times 10 to the 23 atoms of hydrogen with 3 times 10 to the 23 of oxygen, and the number of zeros all gets out of hand and it gets silly. So all Avogadro's number is basically, you say that 1 mole of hydrogen weighs 1 gram. Therefore, one mole of hydrogen reacts with 1 mole of oxygen. So oxygen, because each atom is heavier than hydrogen, it's about 16, I think, 16 times heavier than hydrogen. So 1 gram of, let's say 2 grams of hydrogen will react with 16 grams of oxygen, or 2 moles of hydrogen will react with 1 mole of oxygen to create 1 mole of water, 2 moles of water. And so it's basically a sort of a trick which chemists use to make the maths easier.
Right.
And involve fewer huge numbers.
All right, just to confuse the rest of us, really, I suppose. That's science. Lisa sent an email in to say, if the other volcano next to the volcano that's already erupted, if that erupts, is it true that we'll get an ice age? And if so, how will that affect us? I didn't know there was one next door to it. They were just both grumbling. I'm scared.
There is a volcano right next to the one with the hideous name, which I'm not going to try and pronounce. There's one called Katla, which is very close, and when one erupts, the other one seems to erupt quite soon afterwards. It hasn't done so far. This has in the past has erupted with a bigger eruption, and it would probably have slightly more effect. It might throw a little bit more ash up into the air than the one we've just had. But whether it would create an ice age, volcanoes can reduce the temperature. Mount Pinatubo, which went off in the early 90s, I think, is thought to have reduced the Earth's temperature about half a degree C by a couple of years. And that was a big volcano, but not a huge one by historic standards by any means. There are certainly supervolcanoes which, if they did go off, would pump up so much ash and also sulfate. So as you get sulfates go up and they form little tiny particles in the stratosphere, and they take a long time to come back down. They can cool down the Earth really significantly by 3 or 4 degrees centigrade. That doesn't sound very much, but that means that it would get very cold in the winter here. A big volcano went off in about 1783, and there were all sorts in Iceland, and that caused all sorts of havoc, even in the UK. There were people dying from the fumes coming, which were being blown down here. There were some very, very cold winters, which meant that lots of crops failed. There was supposed to be a year which was called the year without a summer, because there was so much volcanic particles up in the upper atmosphere that the sun never really got through. It was always going through a haze. And it would mean that we'd be very short of food, certainly globally. Probably in this country as well, because if there's no sunlight, plants can't grow and the animals can't eat the plants. It would get very cold. It would have all sorts of negative effects, and it would make stopping flying for a week or so seem completely trivial. They're quite rare, these really big volcanoes, ones that size every few hundred years. Really, really big ones which could actually push us into something very like an ice age. You get things called supervolcanoes. There's one on the Yellowstone Park which could go off, and there's various others. People don't actually know how many of them there are. They could put us into an ice age for years. You get they push out thousands of cubic kilometres of lava all over a period of a few hundred years. It's an absolutely immense amount of lava being pushed out, and then associated with that you get huge amounts of gases coming out and quite a lot of dust and things. And we are living in a fairly volcanically quiet period at the moment. And actually, Iceland seems to have a sort of 80-year cycle. It's sort of, you get quite a much smaller scale again, but as you get a quiet period, which we've just had for the last 50 years, then it gets more active for 20 or 30 years, and it doesn't seem to go quiet for another 30. So probably we're going to get more volcanoes from Iceland, but unlikely that they're going to be they would push it into a really deep ice age. They might drop the temperature a bit for a while.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Let's go to one by email now. This is from Paige, who says, why do my ice cubes shrink in the freezer?
Yes, because I think she's asking that you'd expect that ice cubes, water when it freezes, it expands.
Yeah.
But if you leave your ice cubes in a freezer for a long time, they seem to shrink. This is a process called sublimation, where water can go directly from a solid to a gas. In fact, lots of things can go directly from a solid to a gas, or from a gas to a solid. Going from a gas to a solid is actually how you form snow. The reason why snowflakes are such pretty shapes and not balls is because they were never liquid. So the water vapour went directly from a gas to a solid, and because it was doing that, the molecules can sort of choose where they want to lock onto the little bit of ice which is already there, and so they form beautiful crystals. And then the properties change a bit. It gets a bit more humid, a bit less humid, and so they form different places on the crystals, and you get these beautiful structures. And so basically what's happening is your ice cubes are evaporating very slowly directly from solid to gas and disappearing off into the rest of the world. Sometimes you can actually find it going in the other way, which is why the ice crystals form on the back, where the cooling elements are, and you get all the frost. And frost is the same thing. Water vapour going directly from a vapour to a solid. Sublimation.
How do they stop? How do frost-free fridges work then? In that case,
they don't actually stop the frost forming in the first place. What they do is basically the fridge is a heat pump. It pumps heat from inside the fridge to outside it. And what they do occasionally is they run it the other way. So they pump heat from outside to the inside. They heat up the cooling elements. They get hot enough for for all the ice to melt. It kind of runs down out of the freezer. And then they start cooling again. So basically they sort of defrost themselves very regularly.
Is that energy efficient as well?
It does use a load of energy, and it's not beautifully efficient, but it's more energy efficient than letting the ice build up.
Sure.
Because if you've got a great big thick layer of ice, then it insulates your freezer from the cooling elements, and so they can't cool the freezer so well, so they have to get colder, which uses more energy. So it's a bit of a toss-up between the two of them.
All right. This comes from Derek in Wellingborough on the email. He says, earlier in the week there was a clear blue sky, but with earlier trails from different aircraft that had crisscrossed the sky that had not disappeared, and it seemed to get wider, eventually turning into a haze. But there were other aircraft that appeared to fly through them with their trails that disappeared quickly. What could cause this anomaly?
You certainly do get contrails, the sort of water which is being pushed out by the back of a plane through the engines. That condenses, and then that can form little sort of places for water droplets to grow. So if you've got somewhere which is wanting to form a cloud, there's too much water in the atmosphere for it to really be stable. The water wants to come out and condense. There's nothing for it to condense onto. These little water droplets coming out from the back of the plane can cause more water to condense, and then you get a contrail. And then these contrails can expand, and in fact they can form huge, great clouds. The Met Office saw one occurring in the last 6 months. There was a nice paper about it. And so, yeah, there's that. I would have thought with the other planes flying through and the contrails disappearing, either they were at a slightly different altitude, so they're flying through air which wasn't quite the same as the stuff which was condensing and forming and causing the contrails to expand really well. Slightly different altitude, or the air where the contrail had warmed up a bit, so that the contrail was starting to evaporate anyway. But I think probably the planes at a slightly different altitude, air masses can be quite close together and have very different properties. And so they're probably either flying slightly below or slightly above it, where the air, instead of having too much water in it, didn't have enough, so they just evaporate and the contrails disappear.
Dr. Dave. Now, it's Mula who sent a question in by email and says, I love the programme and I'm now studying environmental science, and this question just popped into my head. How much lava is actually inside the Earth? That's a good one for you to work out, Dave. What do you reckon?
It's a very good question. Essentially, Depends exactly what you mean by lava. If you mean actually molten rock, which is sort of runny and will flow around the place, not a huge amount. The sort of inner core of the Earth, which is sort of first 1,000 kilometres or so, very roughly, is probably quite a lot of that is molten iron, and the inner core is solid again. And outside of that, as far as we know, there's a thing called the mantle. Now, it isn't really molten. It would be molten if it was at surface pressures, but because it's under so much pressure, it actually gets compressed and tends to go more solid. And it does flow. It sort of flows a bit like very, very stiff plasticine. So over millions of years, it will flow, but certainly wouldn't run. It's certainly not what you'd think of as lava in your head. When that comes up near the surface, so sort of in the middle of the oceans, mid-ocean ridges, places like Iceland, then when the pressure is dropped off, bits of it do melt, but actually only a very, very small proportion of it melts, maybe only less than 5%. And then that sort of tends to all get, because there's lots of pressure, that kind of molten stuff tends to get squashed out and squashed up to the surface, and then that molten stuff is what comes out of the top and flows out of the volcanoes. So actually, as a percentage in lava, I mean, many, many, many cubic kilometres, probably thousands of cubic kilometres, but compared to the Earth, a tiny amount. So there's quite a lot, but not as much as you'd expect.
All right, well, let's hope it doesn't come this way. Mulu again has said, I'm sorry, but I've got to ask this question as well. How much smoke from a burning tree is carbon dioxide gas? And what does the smoke of burning wood actually consist of? Dave?
Well, the stuff coming... So if you've got air reacting with wood, wood is basically carbohydrate, like sugar. So basically, if you burn sugar, you're going to get about 1 molecule of water for every molecule of carbon dioxide. So by volume as a gas, about half of the byproducts, which aren't things like nitrogen, which didn't get reacted, are going to be, of the gases, are going to be water, and about half of them are going to be carbon dioxide. By weight, it's going to be a bit more carbon dioxide, probably at least twice as much carbon dioxide, because carbon dioxide is quite a lot heavier than water. So what about all the other stuff? Well, okay, you can see smoke, so it can't all be gases. Some of that is going to be the water condensing and forming little droplets. And the other stuff is going to be all of the things which, when they've burnt, form solids. So there's things like sodium and potassium, so potash and salt in other metals. When you burn metals, they don't form gases, they form solids.
Right.
And so a lot of the smoke is going to be these, basically ash. Ash is another part of it, but ash, which is in very small particles, which goes up into the air. Also, some of it is unburnt wood. So if you heat up wood, it sort of drives off, before it actually all burns and reacts with the oxygen, it drives off sort of lots of chemicals and gases which are made out of carbon and hydrogen and a bit of oxygen in there. This is actually the process that happens when you make charcoal. You're driving off all of these volatile compounds. They burn. In fact, if you have a candle burning and you blow it out, you get the smoke coming out. That's wax vapour. And you can actually, if you do it very quickly, you can relight that wax vapour before it cools down too much, and the flame will sort of jump back to the candle. And so some of the smoke's going to be unburnt wood vapours, these things. Some of it's going to be things which won't burn, so basically ash. Otherwise, some carbon dioxide and some water.
Interesting stuff. Anyway, John has sent a text in saying, Dr. Dave, presumably there are vast areas of our universe which are exposed to continuous sunshine. So why does it get colder the further you go into space? Or have I missed something? John, thank you very much indeed. Good question.
Probably the deeper space you go, so the further away you get away from the sun.
Yeah, the further you go into space, yeah.
Okay.
Yeah.
Basically, if you've got a source of light, if you double the distance you are away from it, if it's giving out light in all directions, it's spread out over 4 times the surface. So if you think about a sphere, if you double the radius of a sphere, its area is going to quadruple. So the same amount of light is spread out over 4 times as much area. So the further away you get, the less intense the sunlight is. So basically there's less sunlight falling onto every square metre of you. So the further out you go, the less sunlight hits you, so the less heating up you get. So, but you've still got the same amount of dark, deep space to radiate energy into, because the Earth is cooling down by radiating heat energy, infrared energy into deep space. So you're losing you can lose the same amount of heat, but you're getting less in, so you're going to cool down until the amount of heat you're losing is the same as the amount you're getting. And so the temperatures drop the further away you get from the sun. why deep space is dark is actually quite interesting, because if you go far enough in any direction you want to hit a star, and the reason for that is because the universe is expanding. The light which is coming towards you has expanded as well, so its wavelength has got longer and less energetic, so colder. In fact, it's got so long that it's actually the temperature is down to about 2.7 degrees of absolute zero, so about minus 270 degrees C.
Wow.
So, yes.
Quite something. Dave, email from Ali. When a wet towel is flicked, it creates a cracking sound like a whip. What is this effect? And why does a wet towel crack louder than a dry one? I can see there's a misspent time going on there. I hate that when somebody gets a tea towel and flicks it at you. It really hurts. Dave.
Okay, this is an effect like it basically is acting like a whip. You get basically a wave travelling down the whip, and because the whip gets thinner and thinner and thinner, the wave actually travels faster and faster and faster, and it carries on getting faster and faster and faster. And with a proper bull whip, the end of that whip can get going so fast that it breaks the speed of sound, and then that basically produces a sonic boom like a jet aircraft, and that sonic boom is very, very loud, and that's what you hear is a really sharp crack. I think with a towel you're probably not actually getting to sonic boom territory, but you do get a sort of wave travelling down the towel which gets faster and faster and faster till the end is moving very, very quickly, and that makes quite a lot of sound, and especially if it comes around and hits itself, then you get a really good crack. I think the main reason why a wet towel is so much louder than a dry one is that partly it's heavier, so there's more energy there, so it's going to be going faster. And also with a dry towel there's not much energy, and also it's quite damp. It's quite well damped. It absorbs quite a lot of energy as you sort of if you wave it. There's a lot of air resistance, and also all of the kind of nice smooth furry bits absorb quite a lot of energy, so a lot of energy is taken out of that wave, so it slows down. There's also less energy in the first place, it's not as heavy, whereas the wet one is nice and heavy, and also I think it's less energy gets taken out of it as the wave goes down.
Very quickly from Sue, because she's just sent a text to say, if an earthquake is so strong it can make the earth wobble on its axis, does this affect our measurements of time?
I think a very, very, very small amount. It can. I mean, huge earthquakes can move the Earth's axis a little bit, and they can change the length of the day. If you, on average, move a load of mass further away from the centre of the Earth, then the Earth's got the same amount of angular momentum, same amount of total rotation. If stuff's further away, then it's got to rotate slower. It's a bit like if you're playing on a roundabout. If you're on the outside of the roundabout, then you're spinning quite slowly. If you kind of pull yourself into the middle, the roundabout actually speeds up. Yep. So if an earthquake moves a load of mass towards the centre of the Earth is going to speed up. If it moves a load of mass further away, it will slow down. But those effects are very, very small, and also lots of less violent things than earthquakes move mass around. Just tectonics in general will push things up and down, push rock up and down very slowly over a period of years, even without earthquakes or without big earthquakes. So these things are changing all the time. How fast the Earth's rotating does change a little bit, and that's part of the reason why the number of leap seconds which are put in at the end of centuries aren't predictable. You can't predict them by mathematics. They actually have to do it by looking and seeing what direction the Earth is pointing in, and seeing how many rotations the Earth has made because of all these little tiny things.
All right.
So it does make a bit of an effect, but not a huge one, not one you'd notice.
One last question that's coming from John very quickly. So with all this fuss about dust clouds, why couldn't the scientists on Iceland or elsewhere have predicted the subsequent chaos?
Because it's difficult to predict, and they can predict volcanoes quite well, but there are quite a lot of volcanoes on Iceland, and the really bad thing with this volcano was both that it was particularly good at throwing ash into the air for into size. It wasn't a particularly big volcano, and also the wind was blowing in the wrong direction. If there had been southerly winds blowing all that ash up into the Arctic, you wouldn't have heard about it.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.